Thank you. So this week we're working on our sea salt lab report. And here are the upfront instructions. So, the written lab reports that successfully address the questions outlined below should expect to receive full credit, okay? Without requiring the reader to be familiar with the questions, should expect to receive full credit. So, please remember that all sections should have headers, be written in full paragraphs, and include none of the questions that are written below. All deviations from, any deviations from the above instructions will likely result in a score of
0.
Yeah, okay, for the submission. Alright, so we're going to go through two sections today, introduction and results. Materials and methods are where?
They're in the notebook.
In your notebook, okay? They're already in your notebook.
Oh, we took
So-
notes on it last week, huh?
So, introduction. We've got 3 questions to answer. First, why is sea salt production important? Second, why is salt, particularly sodium cation, important for the human diet? Now these first two, we haven't really talked about in class, have we? No. But guess what? Scientists have to know why their work is important, and a lot of times they have to just get out there and figure it out for themselves. So, you're not going to worry about class notes, you're going to use... What do you use when you don't know something?
The internet?
Yeah, use Google, right? Get on the internet, figure it out, okay? Now, how did we investigate sea salt production? That's a summary of our methods. So, one sentence that would totally be acceptable, don't write this down, come up with your own, but you could say, to investigate sea salt production, we purified sea salt from filtered ocean water. Done, right? Materials and methods in your notebook. Results section. So the results. First question is, what happened to the water in the beaker upon exposure to the hot plate? So here are beakers after having been put on the hot plate. And what you'll notice about these beakers are that they're caked with salt, okay? They've got this white, cakey, powdery looking salt. I'm going to pass one back from Julian, all the way back to Danny. Danny, bring it up. I'm going to pass one back from Daniel, all the way back to Elijah. Elijah, bring it up. So, I'll get to it in a minute. So, this salt doesn't look like the nice crystalline salt that you have in the grocery store. So when you go to the grocery store, what you find is that the salt in the grocery store has these nice large crystals that you can see really easily with the naked eye. These crystals are really tiny, most of them, and they're powdery. So you wouldn't really be able to get a good look at their crystalline structure unless you examine them under a light microscope. And the reason that the crystalline structure has been disrupted is that the process we use to obtain the crystals, boiling, is a violent process. It's not good for crystal formation. So the bigger crystals that you're used to in your box or your jar of salt from the grocery store, those come from a more gentle evaporation of salt, of ocean water to release the salt. Okay? Good. Thanks, Daniel. Okay, so after all the water evaporated, what you've seen is that salt that's right there in the beaker. You're going to include a table of results, and you're going to include calculations for percent mass salt in ocean water, and percent error. I'm going to show you how to do both of those on the board. Elijah, your question.
I was just going to say, are we doing that online or?
Okay, you're going to submit on Google Classroom, right? On Google Docs. Okay, so now we're going to... Perfect. Now we're going to have our quick lecture on sea salt lab. So this is all going to go in your notebook. Okay, so physical separation, aka sea salt lab, results and introduction, okay? All the instructions, etc. are posted on Google Classroom, but what we need to do is we need to really understand, results and not results and introduction, results and calculations. Results and calculations. Okay, so here are our results. We have a beaker with certain contents. And then this is the mass that we recorded for all of those contents. And notice I've put a little g up here to indicate what unit of measure? Grams. So I don't have to write g's again for all these numbers. Okay? So the beaker contents, first we had an empty beaker. And who would like me to do his or her calculations on the board right now?
Oh, just from what we.
Yeah, do you have your numbers from last time, Elijah?
Yeah.
Good. What was the mass of your empty beaker?
Hold on.
30.
So roughly 30, but we got to know exactly, right?
30.6.
Yeah, it said 30.6
30.6 was the
Without-
empty beaker?
without water.
Okay, 30.6 grams. And then with water,
51.3.
what was it?
51.3.
Okay. And then I'm going to give everybody this result. So Elijah, your beaker was 31.0 grams with salt. Okay, so the salty beaker had a mass of 31.0 grams. All right, so now we're going to do our percent mass sodium chloride calculation. Okay, so percent mass sodium chloride. How do we find percent mass sodium chloride from these numbers, right? We're going to try to find out how much salt is in ocean water from just these numbers. What do we do? So what we need is the mass of the salt divided by the mass of the water. We multiply by 100, right? So how do we find the mass of the salt from these numbers on the board? What will we do? Elijah?
So the mass of the salt was 3.1, so it would be like, or 31.0 over 51.3.
No.
Oh.
So like this is your water. The mass of the salt, you're good for thinking about it, right? Good try. So like the mass of the salt is, look, what's the difference between an empty beaker and a salty beaker?
0.4.
Right, 0.4, but what accounts for that mass of 0.4? What's in the beaker that's making it weigh a little more? The salt, right? So 31.0 minus 30.6, right? So the way this calculation works is it's mass salty minus mass empty divided by, now how do you find the mass of the water? What do? To find the mass of the salt, we said mass of salty beaker minus mass of empty beaker. How do you find out how much mass of water, ocean water, was in your beaker here? Go ahead, Paula. What numbers do you subtract to find the mass of water in this beaker? Okay, so this beaker's got salt, right? This beaker has nothing, just it's empty. Okay, so to find the mass of salt, you subtract the mass of the empty beaker from the salty beaker. Okay, how about find the mass of water? How do you find the mass of water in this beaker?
Subtract the water and the empty.
You subtract what?
The water and the empty.
And the empty. Good, Jason. So you subtract the mass of the empty beaker from the mass of the beaker with water in it, okay? So it's mass with water minus mass empty. And of course, we're going to multiply this by 100. Okay, so let's go ahead and do the calculation. So we get 31.0 minus 30.6 divided by 51.3 minus 30.6 times 100. That equals 0.4 divided by 20.7. Yep, 20.7 times 100. And that's all going to come out to, use my trusty calculator here, that's going to be about 2%. A little bit under. So 0.4 divided by 20.7. You get, yeah. So 1.9%. Okay? So that's our observed result, or that's our experimental value. So this thing is called experimental value. Experimental value, okay? And we're going to need that value to calculate our percent error. So when you're a scientist, oftentimes you don't get the perfect answer, okay? You don't have a perfect result. You have some error involved. And it's fine to have error, but you have to be honest with everybody else about your error. So you have to calculate it, record it, and report it accordingly. That's what we're going to do. So percent error. Okay. So percent error equals the absolute value of experimental value minus accepted value all over accepted value. Okay? And it turns out in this case, the accepted value equals 3.5%. Okay? So ocean water is known to people to be 3.5% sodium chloride by mass. So to calculate our percent error, we go experimental value, that's 1.9%, minus 3.5%, we get the absolute value all over 3.5%, and that's going to give us 1.9 minus 3.5 divided by 3.5. Okay, that gives us 46%. Okay? 46%. So look, one thing I haven't put on the board because we're going to use them interchangeably. If you actually do this calculation, you get 0.46. Okay? That's the same thing as 46%. Mathematically, 0.46 is 46 hundredths. Okay? So that's 46%. I just didn't include the multiply by 100. So if you want the whole number percentage, you multiply this value by 100 to get 46%. Yes?
I'm so confused. Where did you even get the accepted value from?
The accepted value? I Googled that. Okay?
So the accepted...
That's just the value that people, like scientists with better methodologies than the one that we used, actually have gone ahead and calculated this. And honestly, if we were a little more careful, we would calculate it too. So the thing that mucks up our answer is the fact, like literally, that we've done all this boiling. It actually like causes a bunch of salt to like pop out of the beaker while it's boiling, and it puts a bunch of salt on the scale, not on the scale, but on the hot plate and on the countertop. So a lot of our salt just flew out of the beaker literally while we were boiling, right? So the advantage of boiling is that it allows us to get through, like 32 chemistry experiments in 2 days. The disadvantage is that it doesn't give us an accurate result. So we're off by 46% because a lot of our salt boiled out. Okay, it just like popped out and spattered out onto the countertop during evaporation. Questions? All right, so that's it, okay? This is one of those things you have to look up. The accepted value you look up, okay, Google did a fine job in this case. In other cases, I would consult a research paper or a research index, but that wasn't necessary here. And we're all good. So no questions? All right, so you have the next 25 to 30 minutes to work on the results and introduction, and of course materials and methods too for your lab report. Good luck.